Hello and welcome to the Aerospace Ambition Podcast. I'm Kieran, joined by my co-host Marius. As aerospace engineers, we are deeply invested in the intersection of sustainable aviation, climate change and AI. In this episode, we're going to explore the science behind the observation, tracking and detection of condensation trails. The clouds which are made by aircraft predicted to contribute 1 to 2% to human-induced climate change. Throughout this conversation, we'll be guided by an expert in this field. Marius, would you do us the honour of presenting our guest today?
Hi Kieran and hello listeners. Today we are delighted to introduce Rémi Chevallier, a PhD student at Airbus Airline Science, specialized in aviation, data science, optimization and avionics. Rémi recently published an interesting paper on contrail detection using satellite data and air traffic data. He even presented his findings at a recent Sustainable Skies conference. Let's dive into an insightful conversation with him. Welcome, Rémi.
Thanks a lot for having me there.
It's a pleasure to host you. I'd like to kick things off by starting you about this Eurocontrol event. I saw it in the video stream remotely, and it looked very impressive. What was it like presenting there?
Actually, I've never had this kind of occasion, of experience before. This is a huge room full of people. I've been told afterwards that there were up to 4,000 people online. Hopefully, they didn't tell me that before.
I can imagine. I can only imagine. Even on YouTube, I think the views, they increase by the day. So this definitely had an impact. Now, you were basically representing a research institution, but also Airbus.
In Eurocontrol, I presented the work I've done with ENAC mostly, not really with what I've done with Airbus. So ENAC is the French civil aviation university, and my PhD is in collaboration between ENAC and Airbus. So the work I've done in contrail observation is more about scientific things that are done with ENAC.
Right. And it was exactly that paper or parts of the paper that you were presenting on stage. What were the main findings that you presented there?
Maybe one thing we need to all understand before even starting talking about contrail observation is why did we do that, actually? So to predict contrail formation and contrail climate impacts, we need accurate weather forecasts. One of the main things we need, like the weather variables, is relative humidity, temperature, and pressure. That's the three main variables that we need to accurately forecast in order to know which regions will be sensitive for contrail formation. Okay, so one thing, like we all use weather predictions in our daily lives, and you all know that sometimes this prediction could be wrong. And the main problem with contrails is that we need to avoid them, but by avoiding them, we might burn more fuel. So if we avoid a contrail forming region that doesn't exist, we burn more fuel, so we have more CO2 effect, and we don't reduce the climate. We might not reduce the climate impacts of contrails because there wouldn't be one. So one of the main goals of this study was to actually observe contrails in real life in order to be able to say, okay, we can avoid them with enough confidence so that we won't do worse than if we did nothing. That's the main question we try to answer, and that's a very difficult question. So this paper is just the first step, just the first first proposition and the first tool to try to answer this question.
Definitely a difficult question, and yet you made some progress, right, in finding some answers. So if you had to summarize it like really briefly, last slide of your presentation, what were the findings from that research?
I'd say that the findings would be that it is possible to detect contrails, match them, like identify which aircraft produce them. So this is already something very important. We found also that there are a bunch of limitations with this method. I'm using geostationary satellite images. These images have a quite not that good resolution. Don't get me wrong on that. It's the best available at the time, but it's still sometimes not enough to observe accurately contrails. So in this case, we have a bunch of limitations, and observing from geostationary satellite only is not enough, definitely. So we need to combine these images with other sources of information. So that's the second thing. And the third thing is that we can use the resulting data to compare with contrail prediction models and see is there a difference between the prediction and the observations. And the fourth thing is that because we need to combine many different sensors, many different types of observations, this will be very expensive and very time consuming. So it's going to be very difficult for one organization only, even if it's Airbus, to do that on its own. So we need a collaborative approach on the topic. We need to work together on this topic and share information and data in order to be able to solve this problem.
So would you say that that's this is the novelty in your approach, is the fact that you're combining real weather data, you're combining contrail prediction models as well as satellite observations? Is this something that hasn't really been done before? I'd
say that it has already been done in some ways by DLR, so German Research Institute. The new thing in this approach is that I use computer vision, like AI computer vision, machine learning, deep learning to detect contrails. So it's more accurate than what they did. And the way I track the contrails and the way I match them with the flights is quite different as well. So let's say that it's not a completely new approach, but building these three main blocks and combining them together in one tool hasn't been done before. And also the fact that this is just the basis for to allow for combining with other type of sensors. Like you can add information from ground-based images, like ground-based cameras, from LiDARs, anything. So this is the new part.
So I know that Google have a somewhat similar approach to detecting contrails is through their matching algorithms. Can you explain a bit about how your approach may differ from Google's?
Yep, definitely. So first, at the time I created this algorithm, there was no contrail observation dataset freely available. So we had to train a computer vision model without having an actual dataset. So that's a quite tricky question. So we had to generate a dataset based on a synthetic dataset. So it means that we needed to create images that would look like what contrails would actually look like in reality, but without having these contrails in real life. So we used COSIP, which is a contrail simulation algorithm, and we used that to generate images along with a bunch of other methods to generate images that would look like contrails, and we trained our algorithm on it. So that's the first difference with what Google did. Then we are not using exactly the same kind of computer vision algorithms. Basically, what they do, that they detect all the pixels that correspond to contrails. You have one image and you tag each pixel. Is it a contrail or not? My approach is quite different. In my method, basically draws a shape, a polygon around each contrail, each individual contrail. So in some ways, it's easier to use this kind of information afterwards, because already with individual contrails, not a bunch of contrails when they overlap and these kind of things. And the third thing that is very different is the way that I use the tracking and matching algorithms. So this is quite difficult to explain without images, but we did present it in Eurocontrol and also in the European Commission in December.
Yeah.
And basically, I have a method that solves the tracking and the matching of the contrails at the same time. And each process gives information to the other in order to improve the overall results. Whereas Google, they have more data-based approach in which they look at the traffic in real life. Using the air traffic data, they get information on the wind and the uncertainties on the wind. And given this information, they set up filters like my aircraft was there at that time. I see a contrail there. Okay, I will allow for that much difference in angle and that much difference in space, like in that lateral position,
Like a tolerance,
and they filter.
spatial and temporally, I'm guessing.
Yeah, definitely. And mine is not a filter; it's a matching algorithm.
Oh, right.
It's a bit different in the approach, and I'm very curious about like what we'll get like comparing the results in next projects.
Would you say that it helps, or does it hinder the process of detecting two contrails which might be overlapping, or like contrails overlapping with clouds? Because I know that's a big problem with a lot of the approaches that are out there today, is that it's very difficult to distinguish a contrail from a cloud or a contrail from another contrail. So does this help in the way that you're going about this?
Like the fact that I'm using what we call instance segmentation, like drawing a polygon around the object instead of detecting all the pixels, this might help because you don't have to post-process to get, okay, I have two contrails overlapping. Okay, so which pixels is from which contrail? This is a quite tricky question to answer. So I'm not trying to answer that. I just let the algorithm get the answer. I train it to get the answer.
Yeah.
So this is the first difference. And then my method will allow to, for example, if you have two contrails that are parallel, this is a quite tricky case because uncertainties on the wind. If you have two aircraft flying by, both aircraft could have made both contrails according to the filter from Google or the one from DLR, by the way. So my method is taking into account the information about what's around and matches the contrail with the one that is with the aircraft that the most probably created this contrail. This is again quite difficult to explain without images, but we have a higher confidence on the result. However, we also miss more contrails, which means that it's not meant to be used as a monitoring algorithm. You know, we can't monitor all contrails, but we are able to select a bunch of contrails on which we have a very high confidence on the tracking and matching.
So currently it's more of a research tool that will obviously be developed over time and hopefully will become more of an observational tool that maybe airlines can use or flight planners.
Yeah, or MRV or these kind of things.
I'd like to go one step back. We've been told that we are very technical in this podcast and we're trying everything to improve that. So when you said initially you were creating this synthetic data set, right, to have something to train algorithms in the first place, then please help me understand. So COSIP, as far as I understand, gives you basically variables in a grid, right? So this is a physical model that is simulated. And then on the other hand, you have image data, right? And what I understood is that this synthetic data was basically image data. So how does this play together? Maybe on a high level, but still for me to understand.
Okay, so basically what I did, COSIP is able to give you positions of the contrails, of the predicted contrails. It gives the position and it gives some information about the width, the optical depth, and some microphysical properties like ice crystal shapes, concentrations, and everything. So what I would like to do at some point was to try to have something physics based, you know, like equations to get from COSIP to images, but I did not have that. So what I did was that I labeled a bunch of contrails by hand on satellite images, like real ones, and I trained a very simple model to get from microphysics properties predicted by COSIP to the actual images. So this is something very inaccurate in terms of physics, but it is enough to train a model to detect contrails.
Another question I was asking myself, you mentioned it briefly in the presentation as well, was that the algorithms are agnostic to the input data, right? So they could come from many different sensors, and they are also built, you said, with the assumptions that sensors could improve over time.
Yeah, definitely. The main interest of this algorithm compared to the one from DLR, for example, is the fact that you can give it more information. Like the basis, it cannot work without air traffic data, weather data, like wind information, and geostationary satellite images. That's the principle, like that's the basis. And then if you have that, you can add information, for example, with if you have ground cameras, you have a bunch of cameras facing the sky, you detect contrails on these cameras. You can, for example, sometimes you can see contrails forming directly. You can see the aircraft and you can see the very young contrail that just formed. In this case, the matching becomes trivial. You basically saw it happen. So if you see these kind of things, you can just take this information. Okay, I know which aircraft produced the contrail because I saw it. And you give this information to the matching algorithm, and it just removes unknowns from the equation. Because with the geostationary satellites, the main problem is that the resolution is quite low. So you can have up to like 20, I think it's 20 minutes in average between the contrail formation and the first observation of the satellite image. So during these 20 minutes, you basically don't know where the contrail is.
Are you expecting this temporal and spatial resolution of satellites to improve?
So first, the temporal resolution is very good already. We have one picture every 5 minutes over the continental US, every 10 minutes over the full disk, which means that like we have a geostationary satellite. Geostationary satellite is a satellite that basically stays over the same place. And you can take pictures of this same place as soon as you want. So we have like as open source data, like it's free, it's free to use. You can also see it if you want. You can type on your browser, Go's imagery viewer. You can see the same image that I'm using. These images, you have one every 5 minutes over the US and one every 10 minutes for the whole full disk. So this is already great. The main problem is the lateral resolution, because contrails are quite small objects. And GO-16, which is the satellite I'm using, is already the best available. The MTG satellite, Meteosat third generation, that was launched last year, and we're still waiting for the first data to be available, but it's currently under test. But this is going to be the same kind of sensors that is in GO-16, so it's going to be the same resolution. At some point, it might improve, but it's not going to be this year or anytime soon. That's going to take quite a long time, because geostationary satellites are very expensive.
Yeah, so I noticed that in your paper you said that, of course, you're combining your matching algorithm with the COSIP contrail prediction software, which is based on contrail physics. I noticed you said that the matching depends on certain weather factors, so weather parameters that are input to the model, so the actual prediction and the discrepancy between the matching algorithm and their contrail prediction depends on separate weather factors. So could you maybe explain what these factors are, and maybe how well they influence the physical prediction compared to the satellite detection?
Okay, so first in my study, in my paper, I had this, like I combine the matching algorithm with the tracking algorithm, but COSIP is not used as is. The COSIP was used to generate a training data set at the beginning, but then I don't use it anymore.
Oh, I see.
This tracking algorithm, it's using only a very simplistic method with advections. Like basically, I try to predict the positions where a contrail would be if the aircraft produced a contrail. I try to get rid of any of all the weather information that might be predicted wrong. Like the relative humidity is quite uncertain, so I try to get rid of it on my observation. Okay, so in this case, after having this tracking and matching algorithm, I can compare with COSIP, and in this case, it's quite interesting to see the results, because so I haven't run large enough studies so that we can state, okay, this is good, this is bad. It's only I'm only detecting patterns for the moment. For example, contrail prediction will be very accurate in some cases, in some very, very stable weather patterns, when you have very stable regions with a very stable air mass. In this case, contrail prediction will be very accurate. And sometimes when you have smaller regions, more unstable regions, contrail prediction will be way less accurate. So this is the kind of results you will get. And the problematic factor most of the time is relative humidity.
So prediction of ISSRs, as we've spoken about previously. But how about the climate impact? So the radiative forcing estimation. Is there a way to estimate radiative forcing using satellite data?
Yep, there are some methods to do that. So what I've done in my study is basically just trying to get the positions of the contrails and their shape. Then the optical properties of which you can derive radiative forcing, for example, they are much more difficult to get from geostationary satellite observation only. I know that some people in DLR and in Google have worked on a method combining different sensors. They've used low orbit satellite that can actually measure these kind of things, this kind of radiative forcing or like the optical properties. And they trained a machine learning algorithm to reproduce the results of these low orbit satellites. So they have a model to estimate the radiative forcing out of GO-16 or any geostationary satellite like that. But it's not that trivial. That's quite difficult.
So would there be a lot of uncertainties associated with that in the same way that there are with the physical modeling of radiative forcing?
But I don't know, because when you're looking with observation, maybe like you can actually quantify the uncertainties, and like it's
Okay.
I don't know. I think it's going to be like you'll have less uncertainties than with the predictions. And that's why I believe this is very interesting to work together, because I have the positions of the contrail and their shapes, and combining that with methods that can estimate microphysics and climate impact, it's going to be great.
Now we've spoken in very detailed fashion about contrail observation, validation as well, but one could take one step back and think about what are the trade-offs here, right? Well, if we think it through, if we actually implement this in the future, then there are always these trade-offs. You mentioned it, Rémi, in the beginning, briefly when you said there's always additional, fuel, hence additional CO2. So there are some trade-offs, and I've seen many presentations now, all of the presentations at Eurocontrol event, for example, and I would say in every second or third there was this 2021 Lee et al. Paper and this very famous chart that basically, outlined the uncertainties when it comes to non-CO2 effects, also contrails, and then this was heavily quoted. Now, recently, a couple of months ago, there was another paper, and I'm quoting one interesting sentence here, where basically the authors tried to point out the uncertainties when it comes to the mitigation of non-CO2 effects. And one phrase that stuck with me was that there is an appetite amongst some stakeholders for non-CO2 mitigation of aviation effects on climate. Who are they referring to, in your opinion?
I don't exactly know who they are referring to, but I guess there are many people see contrail mitigation, contrail avoidance as a silver bullet to deal with climate change induced by aviation. So, LIRA 2021, what is very important to take into account is the fact that it is fleet based. It is estimating the impacts of contrails since 1950 or something. So it is a fleet-wise approach. It is very different to estimate this impact over 50 years, over the whole fleet. Know that this contrail impact exists, have a bunch of uncertainties that are quantified on this one, and it is very different between that and being actually able to avoid contrails. Because to avoid contrails, you will need to forecast on a flight-wise basis the impacts of contrails. So this is very different. And I think this is the main difference between the two papers by David Lee. The first one is very fleet-wise. It says, okay, there is a climate impact of contrails. And the second one is, okay, indeed, there is a climate impact of contrails. But to be able to mitigate it, we need to take into account that on a flight-wise basis, we are currently maybe not able to predict it accurately enough. I'm not sure if I agree with him, because on the observation side of things, we've seen that in many cases, contrail observation match with contrail prediction. But indeed, in many cases also, you can see that it doesn't work. And I also see loads of people avoiding regions with high energy forcing, just using the output of COSIP. One of the points of David Lee is the fact that is energy forcing is not climate impact. It's a proxy for climate impact, but it's not enough. Sometimes even avoiding regions with high energy forcing will end up in doing things worse than if we did nothing, if we just flown straight. Okay, so this is something very important to me. It's trying to see in which conditions are we confident enough so that we can avoid this contrail and say, okay, I'm sure of it. I won't be worse than just flying straight.
Right. Very important difference to point out.
What would you say are the biggest sources of uncertainty for contrail prediction?
I think the most important source of uncertainty is obviously the weather forecast. But even like since the beginning of this talk, we've only discussed about ERA5 or this kind of sort of information. ERA5 is reanalysis. Reanalysis, it's not something that you can use in operations. Mm-hmm. It's looking backward in time. What is the best estimate of the weather we will have? But backward in time. Sure. If you try to use forecast data, but I put myself in the shoes of the airline. I need to plan my flight 12 hours before takeoff, publish my flight plan at the latest 3 hours before takeoff. That's what's mandatory. So the best information I can get there is the forecast 3 hours before takeoff. Sometimes I have a flight that is maybe, 9 hours. So trying to predict the contrail impact at the end of this flight, taking into account that the fact that you already planned your flight before 3 hours before takeoff, you have a lot of uncertainties because of that. So I think that's the biggest problem. And we need to solve this maybe by using tactical decisions instead of trying to if you can get information during your flight, like new weather data, re-optimize your flights and negotiate with the ATC, with the air traffic control, in order to change your flight and change your strategy mid-flight. Maybe it can solve some of these uncertainties, but it's something quite difficult to implement. And again, 2025, 2028, it's tomorrow. So it's going to be difficult to have something working, changing the air traffic control the way it works by these dates. It's going to be difficult. So yeah, there are loads of uncertainties. Most of them come from the weather data, and some of them will come from air traffic control. And I think that we really should tackle these before implementing anything. But it's possible. We're working on it.
When you say you're working on it, what is the solution that is out there today that is being implemented that solves this in a sufficient manner?
I don't think today there is one. I know that, for example, flight keys is avoiding polygons with that are defined with the highest energy forcing regions. Like you avoid the regions in which you would create contrails that are very high energy forcing. So this is interesting, but again, energy forcing is only a proxy to climate change, and you don't quantify, you don't compare the actual amount of CO2 you emitted, like the impact of the amount of CO2 you emitted with the reduced climate impact of the contrail. It's quite difficult, but the main advantage of flight keys is that they have a very versatile trajectory optimization methods, and they actually work with airlines, they work with ATCs, with network providers. So I think it is very positive that they work towards solving the operations, like the ATC constraints, the airlines constraints, but there will still be some work to do in the climate impacts part of things and the weather forecast part of things.
So when you say radiative forcing and energy forcing of contrails is only a proxy for climate change, can you elaborate on what you mean by that?
That's basically a quote from David Lee's presentation in Eurocontrol. Mm-hmm. What it means is that radiative forcing is basically trying to estimate the difference in the amount of radiation that goes into Earth's atmosphere and the amount of radiation that goes out. If you add a contrail, you modify this balance. And that's basically what radiative forcing describes. It's not climate impact. Climate impact, it's going to be the long-term change in temperature of the surface, for example.
It's going from the prediction of the shape and the properties of the contrail all the way towards predicting its relative forcing. So what are the instantaneous climate effects of the contrail? And then finally down to what is the actual temperature change induced by that contrail. So the global temperature change induced by a single contrail, which is of course going to be probably picokelvin, right? So tiny amounts, but still non-negligible nonetheless.
I see a lot of different uncertainties, actually. The first one is on the formation of the contrail. Then there's one on the way it behaves, like its evolution, only on the shape and properties. Then there's one on trying to get the radiative forcing. And then there's one to go from radiative forcing to climate impact. So that's the first problem. Like we have loads of uncertainties only on the contrail climate impact prediction. And then we have all the constraints and uncertainties related to operations and air traffic management. So I believe these could be solved separately for the moment. And that's why I believe that the work with flight keys, breakthrough, Google and Airbus is very interesting, because we work on solving these operation constraints and having a work on the other side of things with the climate impact with so many different actors as well. It's very interesting. And I think we'll get there.
You mentioned that Airbus is involved in more of the operational feasibility side of it. So could you maybe talk a bit more about the exact role of Airbus in contrail avoidance? And of course, they're a manufacturer that is not necessarily in their interest to get involved in routing of aircraft and the operations of aircraft. So can you explain a bit about why Airbus is so interested in this concept?
Actually, I'm just a PhD student, so I can't really talk in the name of Airbus, But but I believe that it is still interesting. Like it is interesting for Airbus to have to work on all what's related to air traffic transport, air transport. Sorry. So it's going to be interesting for solving operational constraints, adapting the aircraft to future operational constraints. It's going to be interesting also to know if they need to equip aircraft with new sensors.
Yep.
And also because it's a very important topic for aviation, like civil aviation. So indeed, people like Airbus and Boeing will be included and will be part of it. And there are some very interesting European projects. For example, Ciconia, the one I'm working with.
Mm-hmm.
In Ciconia project, Boeing and Airbus are working together on this topic. I find it amazing, actually.
And the Geese project as well, which is formerly Fellow Fly.
Yeah, it's not exactly on contrails. It's not on non-CO2 topics.
Yeah, so it's the formation flying, right?
More about the CO2 effects. But indeed, there are loads of different climate impact related projects in which different actors both in industry and research in academia are working together. And I find it great, actually.
Rémi, you've mentioned flight keys several times now, and it's funny because we had Alejandra on our show, and we have this tradition. And the tradition is that one guest passes on a question to the next, and she did pass on a question to you. So I'm going to read out the question that she is asking you. Are you ready?
Yep, I am.
Rémi, do you, in your most honest opinion, think that we will have incorporated contrail avoidance commercially in the next 5 years?
Okay, that's a kind of tricky question. Actually, 5 years, it's tomorrow, as I said. I think that we won't have like the most sophisticated, the most accurate methods for contrail avoidance and contrail mitigation available in 2, 3, 5 years. But I think we can still do something. When we discussed a bit about that earlier, having contrail observation during my study, I was able to detect some patterns in which contrail prediction was actually very accurate. So if we manage to do that automatically, being able to give a score on contrail confidence, like contrail prediction confidence, we can implement something in which we only avoid the regions in which we have high confidence. This is something possible. We need to solve this question. This is something that is not implemented yet. So we need to build this method. And we also need to 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 solve some operational problems. For example, in Europe, it's going to be very difficult to avoid contrails for all aircraft, even avoiding high climate impact regions, because of the way the airspace is built, or at least it will take some adjustments and modifications of the air traffic management system. So one possible solution would be to start with less constrained airspaces above oceans, above these kind of things. So yes, Alejandra, we can in 5 years have contrail avoidance, but it's going to be, we're not going to avoid all the high impact regions, and we won't do that everywhere. But I believe we can do that, but we need to select high confidence regions, and we need to avoid them in not so constrained airspaces.
Great. I think this was the most personal answer we had ever. Now, as this podcast will continue, of course, you also have the chance now to be spontaneous and pass on a question. Our next guest will be Joachim Mayholm. Which question comes to your mind that could be interesting to ask Joachim?
Okay, so Joachim, how do you think we can overcome the operational constraints that are involved in contrail avoidance procedures and contrail avoidance systems, and also deal with the uncertainties on the weather, even if it's not exactly related to our field?
Very technical question to round off a highly technical discussion. But I think it's been extremely valuable for people who are somewhat versed in this field already, and hopefully we've looped back to the lower level fundamentals for people who are just interested and trying to learn a bit more about this field. So I think with that, we can round off the session today. Thanks very much for taking the time to speak with us, Rémi.
Thank you for having me. Thanks a lot.
Thank you so much, Rémi. I recommend everyone to watch your presentation at Eurocontrol. We're going to link it in the show notes, the precise position where you spoke. Other than that, Kieran, Rémi, thank you so much, and talk to you soon.
Bye.
Bye.
Bye.